Everyone, in this video we're going to talk about several different aspects of analyzing functions. Okay, we talk a lot about functions and especially their graphs, graph theory, and our math classes, but what are some specific things that I would like to be able to draw conclusions about with a graph, or at least draw attention to? Okay, so a lot of vocabulary in this video. You want to be writing those things down, and several good examples of graphs and techniques that we use to determine some things about a functional relationship. Starting over here on the left, okay? So again, we're going to revisit this idea of domain and range, okay? And so in the last video, we discussed what domain and range were, but simply domain and range obtained from a graph, how would that look, okay? But domain, recall, domain was the set of all x values that when placed into a function caused the function not to be undefined or not to yield an imaginary value. In other words, they're all the x values from left to right that my graph actually uses. So it's actually really a lot easier to obtain that information, at least in my opinion, by looking at the graph than it is to find it algebraically sometimes. So let's take into consideration, first of all, this graph right here that I've kind of drawn in. And I do want to point out, you know, I want to emphasize this right here, but this spot over here is an open dot, okay? Which means it didn't actually include this x value of 5, and it didn't actually include, at this spot, a y value of, looks like, what would be about 2. But the fact of the matter is this. When we say domain of a graph, what we're really saying is from left to right, what were all the x values that tended to get used, okay? So you'll notice here that I'm going to put a bracket there and an open parenthesis here, but from an x value of -1 all the way over here to an x value of 5, and not actually including 5, because this was an open dot. There was no substance there. It's everything up to but not including 5. What we necessarily see is that those were all the values on the page that we had our pencil down, and so therefore those were all the x values for which our function is defined. So looking at it this way, we say domain of this function is basically how far from left to right it spans, or for what intervals of x values was our function being laid down or drawn. So we say on an interval starting at -1 and including -1, because this x value -1 right here actually did pop out this y value. There's a solid dot there. But from -1, all of the x values between there and an x value of 5 worked. Now you notice I'll put an open parenthesis here, but we say, okay, it didn't actually include the x value of 5. So for that reason, we cannot put a bracket there like we did on this -1. But really all this is saying is, on this interval, those are all the x values that you actually drew your function on. Okay? So when we talk about range, it's the same kind of idea, except we're talking from top to bottom. So our function kind of spanned from here to here, and we'll say that, you know, we've got this y value here is -3. But how far did our function span in a y direction? In other words, what were all the y values that actually got used? So we say range-wise, it started at the lowest y value it had was -3, and it included this y value of -3 because we had a solid dot here. And it goes from -3 all the way up to a y value of +3, and including that value. So again, all we're stating are all of the y values, or on which interval of y values our function was defined. Okay. Now, real quick, I just want to bring up a couple more vocab terms here, but we're gonna use these often later on. So you'll notice that this was on this graph the highest spot, or at least the highest y value. And on this graph, this was the lowest y value. We're going to give this a name. We're going to call these extrema. Extrema. Of course, you can see the Latin involved in this. Extreme, you might think. But we're going to refer to this top y value, the highest it ever went, as a relative. Okay? So, and we could say absolute because it is the highest spot. But what we're going to do is we're going to call this a relative extrema, but specifically, what we'd like to refer to this as a relative kind of maximum. Okay, so the word that we're actually going to use on this one is a relative maximum. Just do the Latin theme, maximum. I'll go back and get that I there. We're going to refer to this one here as a relative minimum. Okay, maybe this function is describing minimum. Sorry. maybe it's describing temperature within a certain time period, and we say this would be max temperature, min temperature, but maybe not the absolute max or min, but we say relative extrema, okay? So, yeah, so we want to know those things about domain and range and maxes and mins in general. So next we're going to talk about this idea of a vertical line test. Okay, so in previous videos we discussed this idea of a function as being a rule that is defined that necessarily, basically, is defined in such a way that for every x value you plug into the function, it spits out one and only one y value, okay? And so we drew some pictures. We said there were different ways to determine this and different representations, but the first thing I want to point out is this. And for this relation right here, okay, between x and y, you'll notice that we'll give this x value a name, we'll call it x, okay? But when we plug x into this function, you'll notice that not only did it head up to this y value right here, but it headed down to this y value down here. In other words, there existed, it only takes an x value for which it mapped onto two separate y values. And of course, by definition of a function, we said a function must be 1 to 1. That is, every x value is only allowed to go to one y value. You'll notice, though, that since this x value went to two different y values, and this is a single x value, these 2 points right here should be situated quite vertically on top of one another. So what we're going to do is we're going to define what we call the vertical line test. And the vertical line test does no more than say that if you can draw a vertical line anywhere, over some specific x value, and let's say it hits a function 2 or more times. So for example, it hit my function 2 times here, and 2 times here, and it doesn't matter that it doesn't hit it 2 or more times over here, or that if I drew in a vertical line right there, it would only hit it once. It only takes one x value, or in this case several, but if you can draw a vertical line anywhere and it hits your graph 2 or more times, then we would say this is not a function. Okay. So let's take a look at the second one here. I mean, the question is, are there any spots where we could draw a vertical line where we'd hit the graph 2 or more times? And in this instance, no. Every x value maps to 1 and only one y value. So using the vertical line test, we can conclude that this is a function. And then this last one over here, this one usually gets people, but we say, vertical line test. Is there anywhere you can draw a vertical line that hits your graph 2 or more times? And of course, if I drew it at this x value right here, it only hits it once. And if I drew it even at this x value right here, it hits it only once. And then people say, well, guess what? If I draw a vertical line right here, it doesn't even hit the graph. And you know what? That's okay. All this means is, on this interval from right here to right here, that's a set of x values for which my function is undefined. There were no y values that came out. Okay, so we can have undefined spots. We can have x values that are not in the domain. Simply all we're checking is, could we draw a vertical line anywhere that it hit our graph 2 or more times? And if the answer is no, then we have to admit that it is a function. Okay. The last thing we're going to talk about today are the zeros of a function and the intervals for which a function is increasing and decreasing. Okay. And then the third possibility is we say a function is constant. But simply, looking at this, we say these are spots where our graph has maybe a positive slope, a negative slope, or a slope of 0. It is flat. So what we're trying to do is locate the interval of x values for which our function is increasing, decreasing, or constant. So let's take a look at this first function over here, and we say, okay, you'll notice that from left to right, our function is no matter what, from left to right, from an x value of negative infinity all the way over to an x value of positive infinity. Okay, our graph is always having an increasing rate of change here, or a positive slope. So we say that this function is increasing, and we want to define an interval of x values. So we say increasing for all x from negative infinity, but not including negative infinity, out to positive infinity, okay? This graph is always increasing. Over here it gets a little bit different though. You're going to notice that our graph from negative infinity up into a certain spot, okay, up into this spot right there, it's increasing, but then it starts to go downhill with a negative slope, okay? So it goes basically from a positive slope through a slope of 0 here, and then back down to a negative slope, and it decreases all the way till it gets to this spot right here, and then tends to increase again. So to write this, here's how we want to write it. We're just identifying all of the x values for which our function is increasing and for which it's decreasing. So in this case, you'll notice it was increasing from negative infinity up to but not including -2. And the reason why I say not including at -2 is because at exactly an x value of -2, our slope of our graph topped off and it became a neutral slope. It was neither increasing nor decreasing. So we say it's not increasing exactly at -2, so we cannot put a closed bracket here. And then it decreases for a while. So it decreases from -2 but not including -2 up to +2 but not including an x value of +2. And then, we go back up to increasing, and we say, okay, so it starts up again when it gets to an x value of 2, but not including it, and then all the way out for the rest of the time here, it goes back to increasing. Okay? So the last thing I'll write over here is this. We can see on this function here that from here to here it's increasing, and then over here it's decreasing. And that's going to get cut off there. But from right here to here, you'll notice it has a 0 slope. We're going to refer to this as the function being a constant rate of change. Okay, it's maintaining a constant y value of 1. So we say increasing. In this instance, increasing on this graph, we'd say it increased from an x value from way out to the left at -infinity, but not including it, up to, but not including +1. Or excuse me. I don't want to confuse anybody here. This x value right here is 0, okay? So, but up to and not including 0. And we say constant. Our function was not increasing nor decreasing. It was constant from 0, so exactly at 0, out to an x value of 2. And including 2, it was flat. And then we say it switches back to decreasing, okay? On the interval from an x value of 2, not including 2, because it was at a 0 slope at exactly 2, but everything up to 2, all the way out to the right, to an x value of infinity. So just kind of a few things we look at when we analyze